Welcome back. Let's look at the following theorem. If A has a finite order n, then the subgroup generated by A contains n distinct elements, E, A squared, dot dot dot, a to the n minus 1. And in particular, a to the I and a to the j are equal if and only if n divides I minus j. And the statement that n divides I minus j is the same as saying that I is congruent to j mod n. Put differently, what we are saying here is that if A has finite order n, then the powers a to the 0, a to the 1, up to a to the n minus 1 are the distinct powers of A, and are distinct powers of A, and any other power a to the k of A is one of these n powers. Okay, so to prove this theorem, pretty much we have to prove this this statement right here, that a to the I is equal to a to the j if and only if n divides I minus j, or a to the I and a to the j are equal if and only if I is congruent to j mod n. Because once we prove this, notice that none of these powers here are congruent to each other mod n. So if we prove this, then we know that these are distinct powers of A. And then any other power of A, well, if I take any other power of A, then the exponent would be congruent to one of these exponents here, modulo n. So then any other power of A would be equal to one of these n powers. So pretty much we need to simply prove this statement right here. Okay, so the assumption of the theorem is that the order of A is n, and A is an element of a group G. If a to the I and a to the j are equal, then obviously if I multiply both sides by the inverse of a to the j, that is a to the negative j, then I get a to the I minus j is the identity. So by the previous theorem, we know that I minus j would be divisible by n. So n divides I minus j. So what we have obtained then, if a to the I and a to the j are the same, then the order of A n divides I minus j. Remember, we had a if and only if statement, so the opposite, I need to prove the opposite as well. On the other hand, if n divides I minus j, then obviously I can express I as j plus a multiple of n, and then a to the I would be the same as a to the j plus nk, which by laws of exponents is a to the j times a to the nk. But a to the nk would be the identity because n is the order of A, so I get a to the j here. So if n divides a to the j, if n divides I minus j, then a to the I and a to the j are the same. So what we have completed is the proof of this statement right here. And like I have explained already, this also proves this line right here, that these are the subgroup generated by A contains only n distinct powers of A. So notice that none of these exponents here are congruent to each other mod n. So by this, they will be distinct, and if I take any other power of a, then the exponent would be equal to one of the numbers from 1 to n minus 1 mod n. So any other power of a would be equal to one of them. So and here I kind of explain that a little bit more. I'll let you read through that. Now let's look at a corollary. So this is what we have proved. So notice that if A has order n, then the subgroup generated by A has n distinct elements here. So the order of this subgroup, that is the number of elements of this subgroup, is the same as the order of A. So we're just going to state that in a corollary. So the order of A, which means that the least positive power of A that is equal to the identity, is the same as the order of the subgroup generated by A, which means the number of elements in the subgroup generated by A. I want to finish this video by making two remarks: that the multiplication in the subgroup generated by A is essentially done by using addition mod n if n is the order of A. That is, what I mean by that is, if I am multiplying a to the I and a to the j, that's the same as a to the power I plus j mod n. Similarly, the multiplication, if A has infinite order, then multiplication in the subgroup generated by A is essentially done by using addition in Z. That is, a to the I times a to the j is a to the I plus j. So in the exponent here, notice that we are just adding the exponents here. Here we are adding the exponents modulo n. Okay, so I will stop the video here. In the next video, we'll be looking at a very important theorem on cyclic groups.